Let's do some practice, converting from a name to a formula and from a formula to a name for both ionic and covalent compounds. Now, first off, how do we identify the difference? How do we know when a compound is going to be covalent or ionic? Well, ionic compounds are always going to contain a cation plus an anion. And a cation is going to be a metal, where an anion is going to be a non-metal. Now, there are some notable exceptions to this, like permanganate or chromate, but while those are anions that have metals in them, they are also still going to have nonmetals in them. So a quick way you can figure out if something is ionic is if it has a metal and a nonmetal. So metal plus a nonmetal. Now, what about covalent? Well, a covalent molecule, now because covalent molecules are always sharing their electrons, they're going to be bonding between nonmetals. Because nonmetals are close enough to a full octet where sharing electrons could actually get them there. So let's look at these. Let's look at metals versus nonmetals. If I look at a periodic table here, where are my metals? Well, my metals are going to be anything. I'm going to draw a little staircase here. Okay, so we've got a staircase. So this right here, what I'm circling here, plus hydrogen, is going to be our non-metals. So this is non-metals. Everything else on the periodic table, so everything else, let's do it in pink, everything else is a metal. All of this stuff, all of these are metals. When they are by themselves, a pile of manganese is going to make metallic bonds. A pile of beryllium is going to make metallic bonds. Nickel, a bunch of metallic bonds, okay? Where these nonmetals, those are all going to be participating in covalent. So if I only have nonmetals, it is covalent every time. So we could go up here and figure that out really quickly. So first off, on top, we've got pentaphosphorus decoxide. Well, oxygen and phosphorus, those are both nonmetals. So this is going to be covalent. Copper, nitrate. Copper is a metal. Nitrate is going to have some nitrogen, which is a nonmetal. So that's going to be ionic. Sodium bicarbonate. Sodium is a metal. Carbon in the carbonate, that is going to be a nonmetal, so it's going to be ionic. Carbon tetrachloride. Carbon and chlorine are both nonmetals, so that is covalent. Then iron and hypochlorite. Chloride is going to have chlorine, so that's going to be ionic. Iron is a metal. Here I've got Sn, that's tin, and then C2O4, carbon, oxygen, those are nonmetals. This is going to be ionic. Zinc is a metal, oxygen is a nonmetal. There we go, we know we've got both, so it's going to be ionic. Calcium, phosphorus, metal and a nonmetal, another ionic. P is phosphorus, Cl is chlorine, so this is going to be covalent. NH4SCN, ooh, now this one is a little challenging because all of these are nonmetals, so one might think covalent. But if we are familiar with our polyatomic ions, NH4, this right here, is ammonium. And this SCN right here is thiocyanate. This is thiocyanate. These are both polyatomic ions. And so even though there's no nonmetals here, this is going to be an exception to our shortcut. That won't happen very often, and it'll pretty much only happen with ammonium. So memorize ammonium, and whenever you see NH4, know that this is NH4+. This is going to be an ionic compound. And I've already written the name down here, but let's go back up here and start fresh with pentaphosphorus decoxide. Let's actually put some formulas to these. Since I know that this is covalent, I can just follow my covalent naming rules. And so this is going to be pentaphosphorus. It's going to be P5 Dec oxide, that's going to be O10. Dec means 10. There you go, P5O10. That's our answer. Now, copper 1 nitrate. Now, this is going to be copper 1, right? Remember that our copper 1, that 1 goes with our copper. That means I've got Cu+. And then nitrate. What is nitrate? I might have to look at my sheet for polyatomic anions. If I do that, I'll see that nitrate is NO3 minus 1. I'll write that over here, NO3 minus. So that's my first step in putting a formula to these ionic compounds. Because this Cu plus and this NO3 minus, those charges will then need to balance out. Now, fortunately here it's plus 1 and minus 1, so they balance out 1 to 1. So this is CuNO3. Sodium bicarbonate. Well, sodium is a metal here. This is going to be Na plus. Bicarbonate, I might need to find that on my data sheet. Bicarbonate is also called hydrogen carbonate, but you will never see it as that. You will always see bicarbonate, but that's the formula HCO3 minus. So this is going to be NaHCO3, sodium bicarbonate. And this is actually baking soda. This is what baking soda is made of. It's a fantastic substance. Carbon tetrachloride. Now we said this was covalent, so carbon, it's just going to be C. Tetrachloride is going to be Cl, and tetra means 4. Great. Iron 3 hypochlorite. Once again, I've got iron 3, so I know this is Fe3+, and hypochlorite. I'm going to need to find that. Hypochlorite. Hypochlorite is going to be ClO minus. So these charges need to balance. So that means I'm going to need 3 ClOs to balance my Fe3. So I've got Fe, then I'm going to put this in parentheses, ClO3. So there's my iron 3 hypochlorite. So now let's go from a formula to a name. This is Sn, so this is going to be tin. So then this is tin. And when I look on my ionic periodic table, I can see that tin could be a charge of +2 or a charge of +4. So that means I'm going to need some Roman numerals here. How do we figure out a Roman numerals? Well, I'm going to find C2O4 first, okay? So what is C2O4? C2O4 is oxalate. Oxalate. And oxalate has a charge of -2. This is a -2 charge, and I have 2 of them here. So I take my charge times the number of ions that I have, and that will tell me that this total side over here was -4. 2 times 2 is 4. So that means that this tin is balancing out a -4. So this tin has to be a +4, because there's only one of them. So this tin would be tin 4 oxalate. Now how about this one, ZnOH2? Well, Zn is zinc. And if I look at my ionic periodic table, I can see that zinc only has one option. It's only ever going to be +2. So I don't need to do anything special. All I need to do is look up what OH is. And OH is going to be a polyatomic anion with a charge of -1, called hydroxide. Hydroxide is one of the ones that you'll definitely want to memorize, along with bicarbonate, nitrate, chlorate, things like that. Phosphate's another one that you're going to want to memorize. This is calcium. So this is Ca3. This is going to be calcium. If I look it up, I see that calcium only ever has a +2 charge, so I don't need to specify that with Roman numerals. Then PO4 is phosphate. Now notice, I didn't care about these numbers here. The only time I cared about them is if I need to figure out Roman numerals for something. But since calcium is always a +2, it doesn't matter. So these numbers here, these are coming from the charges on the calcium and the phosphate. So when I write the name out, this calcium phosphate always means Ca3PO4 2. I never need to specify that in the name for ionic compounds. Okay? The only thing I would ever specify with a number would be the charge of a cation. Now we're on to PCl5. This is covalent, so P is phosphorus, and it's 1, so that would normally be mono, but it's the first word, so we're going to say just phosphorus. Phosphorus. And then Cl5 is going to be pentachloride. Now this last one I've already written out down here. but let's just write it on the line. This is going to be ammonium. Ammonium is my NH4. It's the positive cation. And then thiocyanate. Okay, thiocyanate, ammonium thiocyanate. That is this chemical structure. So ammonium is going to be pretty much our only exception to this rule of metal plus a nonmetal. So commit ammonium to memory so that whenever you see it, you know, yep, that's still going to be an ionic compound. All right.